All right, we continue with how the encoder and decoder works. Now, as I was explaining, for my encoder, I have 2 to the power of n inputs, which produces n outputs. For my decoder, I have n inputs producing 2 to the power of n outputs. In my example, I have n is equals to 2. Right, I was saying, if I want to send information in this example, it means I've sent information B. However, if I put my receiver here without decoding what the information is, my receiver would not understand what is 01. What is that? So the receiver has a decoder to decode what does this 01 mean. Now, how decoding goes is exactly the opposite of encoding. We now have n inputs and to the power of n outputs. So if I have a 01 here, my decoder will align my 01 here, and I know I will receive information B. Here, I know I've sent information B. That's how the two work. An example on designing in an encoder. We're going to design a decimal to BCD encoder. We're going to design a decimal to BCD encoder. What does it look like? Decimal to BCD encoder. We have 8 inputs, 16, I mean. They're supposed to be 16, but let me just put 0, 1, 2, 3, 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. All right. BCD. Let me just put up to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4. Let us begin with 16 for encoder. We have a 16 to 4 encoder there, and we're going to apply it when application a decimal to BCD encoder. All right, so what do we have in the inputs? We have 16 inputs according to our 2 to the power of n. It means we have 4 outputs. Right? If you want to make a decimal to BCD encoder, we now have our decimal numbers here. 0, 1, 2, 3, 4, up to 9. What will our output be? We go to the truth table. Uh, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say our output, we have output 1, 0, output 1, output 2, output 3, output 0, 1, 2, 3. Very much easier to explain if you have a clear picture already of the truth table, for example. Right. For 0, our output will be 0 in BCD. Which means here we have 0, 0, 0, 0. For 1, normal BCD representation. 2, right. So what this means, if my output, for every output I have 0, 0, 0, 0, I know the number which is being sent is 0. If I was to put a decoder here, a 4 to 16 decoder, I will know if a 0, 0, 0 is sent, it means it's received here. I've sent a 0. If a 0010 is sent, if I receive this, it means this is a 2. That's how an encoder can be applied. Instead of having 16, in this case, 9 inputs and 9 outputs, I can represent all these 9 inputs using only 4 outputs. I can represent all the inputs 2 to the power of n inputs using only n outputs. So if I am to draw a logic diagram for this, the truth table, I continue doing the same in BCD. So 3 is 0, 1, nope, 0, 0, 1, 1. And I continue until I reach 9. What is my truth table going to look like? I identify these ones, these ones, these ones, these ones. Easiest way is drawing a K-map for each output. With the K-map, we can then go and find the expressions. I will leave that for you. Just a minute. Okay, and that is how the encoder works. Instead of having 2 to the power of n lines or channels which transmit information, we can transmit that information using n lines. How do you do that though? You need a circuit between here. What is that circuit? Encoder. Applications. Applications. Let's talk of applications of both the encoder and the decoder. We have microprocessor memory systems. Memory systems, it is used to select different memory bank, different bank of memory. All right, example. This is a decoder, right? If I select 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. If I select input 0, 1, it means in my bank of memory, whatever it is, I go and select this one, 0, 1, here. This is my memory here. My memory has all this. But with the use of the decoder, in this case. If I input a 01, it means I can only access this memory. Applications of decoders. My laptop, I've opened an application, Zoom. Let's say Zoom, it is a binary representation 01. Every time I open Zoom and I upload a folder, where does it get that memory? It goes and select here, which will represent your Zoom, bigger picture. Everything, how this computer is working, believe me, logic gates. We can use a decoder. A decoder is working somewhere there. Right. Selecting different devices in input output processor systems. Selecting different devices. I think everything deals with selecting when we want to explain how the encoders and decoders work. It dwells with selecting. From this, if I change the input to 1, 1, it means I'm selecting something else. So any problem you have which needs some selecting, you can design a circuit in the form of an encoder or a decoder to help you. And I think that is that for encoders and decoders. Any questions, any comments? Not much information to put out here. I need to move to rather more important things. Questions? Or something else?
Se ndandikumburoka kubvunza kuti
42. Yes.
mati first application yedecoder yo mati ichi ine memory mukati.
Selecting different banks of memory in a microprocessor. In a microprocessor,
Thank you.
What is a microprocessor? A bunch of logic gates. It is just a bunch of logic gates. It has memory, RAM, bunch of logic gates, RAM on your computer, bunch of logic gates. It has memory. How do you select different types of memory in your random access memory? Logic gates. Start thinking beyond the 1 zeros and the 1 ones and the decoders. Start thinking microprocessors. Bunch of logic gates. All right. We can move on to the multiplexer. Another example of a combinational circuit. Mux, a multiplexer. This is a circuit that accepts multiple inputs, but it gives only one output. So we have multiple inputs, but one output. Logic diagram. Input 1, 2, 3. We have selectors. Selector 0, selector 1. This is a multiplexer. Multiple inputs, I0, I1, I2, and I3 with only one output, Y. The MUX device allows digital information from several sources to be routed on a single line for transmission over that line to a common destination. It is also called the data selector because it has a data select input which permits digital data on any one of the inputs to be switched to the output line. One of the
Sorry,
four
sir.
inputs, yes,
Please repeat your statement. You said it allows digital information to be transformed to one line.
nope, don't take notes when I'm reading. Believe me.
Oh.
Don't take notes. One of the, just listen, one of the, because I'm reading something here, one of the 4 inputs will be connected to the output based on the combination of the data select inputs. When I am reading, don't take notes. When I'm explaining though, try picking up a few things. So I'll just read a paragraph here. Now I'll go and explain how the MUX works. It works sort of, it seems I already explained it a bit when I explained the decoder. All right, the MUX, it has 4, this one, this is a 4 times 1 MUX example. This is a 4 times 1 MUX. Multiple inputs, only 1 output. I think the difference in explaining this with the 4-2, what is this? An encoder, right? This is not only 1, but it sort of works in the same way. Now, how does this one work? I'll let the timetables and the logic expressions explain that. The truth tables, not timetables, sorry. For my truth table, I have my selectors. S0 and S1. 0, 1, 0, 1, 0, 0, 1, 1. For my output, I have Y. When the selector is 0, 0, let's say the output is output 0, output 1, output 2, output 3. When my selectors are on 0, 0, it means my input is input 0. If it's 0, 1, my selectors, it means input 1, input 2, input 3. Data output is 0 if S1 is equals to 0, S0 is equals to 0, etc., etc. For my output Y, what will be Y? Y will be, there is an output for every input in a MUX. This is output 0. It is my output 0 multiplied by S0, S1, bar. If I had a 1 here, my output is something like this. Y, 1, 1, 1, 1. It means I have this input coming out as the sum of all these inputs. Equations explains much better. Y is the sum of all the inputs because Y is only one output. What are the sum of all the inputs in terms of my outputs I put out here? O0, O1, O2, O3. They will look like this. A lot of information. A sum plus O1 plus O2 S0, S1 plus O3 S0, S1. So you see my output, even if I have 4 inputs here, my output will only be 1, which is the sum of all my inputs. which is the sum of all, a combination of all my inputs. I can then go and draw the logic diagram, which is simple actually. I have how many inputs? 4, I0, I1, I2, I3. My output here is in terms of what? My input. This equation can also be the same as this. My output is in terms of that input. I have selectors S1, S0. For my first output on a stream of inputs is I0, S0 bar, S1 bar. It means I have a bar here, I have a bar here, and I have I0. This all on an end. I do the next one all on an end, the next one all on an end, and all of them, they are being added. They go on to an OR gate, all of them. And I have Y. This will be my logic diagram. So if I don't have information here, I'll still get Y, which is the sum of the rest. If I don't have information here, Y is the sum of the rest. Applications, probably a better picture from applications. This is a mux, multiple inputs, one output, 0, 1, 2, 3. In communication systems, the multiplexer increases the efficiency of the system because it allows a process of transmitting different types of data at the same time. So for example, if I want to transmit sound, internet data, voice at the same time, what else can I put here? Nothing. I want to transmit these three at the same time. What do I do? Instead of having sound from position A to position B, if instead of having sound, each channel, data each channel, voice each channel, what do? I put a mux. Now I have sound, data, voice being combined. Output, only one output. Being transmitted, one channel. When it reaches the output, I put up a demultiplexer. The same way I have an encoder and a decoder, I have a mux and a demux. And with that, I'm led to the demux, which does the inverse process of the multiplexer. Now I have one input with multiple outputs. So in my example, let's say my input Y now is equals to data plus voice plus what else? Sound plus X. With my selectors here, I now know if my selector is 0, 0, my output will probably be data only. If my selector is 0, 1 here, it means my output at this one will be voice only. The same here, it will be sound only. Here, X. So if I want to collect them separately, I can using these selectors. Application, transmission of the mux. In transmission, instead of having multiple channels, I can only have one channel transmitting these three here. How do I do that? I make use of the multiplexer. Telephone lines, multiple audio signals are integrated on a single line of transmission. Very sorry, Guane, computer engineering, software engineering, and the next. Examples prepared only for telecommunications students. Telecommunications. Ever wondered how you have only one transmission line handling all the voice traffic from Harare? This is a telephone line with 4, I think, transmission lines, right? This line is probably holding person A, B, C, D code at the same time. This transmission line, it transmits the information of all these people at the same time. How does it do that? Without the multiplexer, it means I will have to make use of all the 4 lines here. A uses this one, B uses this one, C this one, D this one. With the use of the multiplexer though, all of them are summed to one output. Same way we can have truth tables, expressions, logic diagrams when explaining, when designing. If I want to design a multiplexer, same way I can have all those truth tables, logic expressions, and my circuit diagrams, then the design for the demix. However, what I want you to dwell on here is the applications. Understand what is a multiplexer. Understand what is a multiplexer. Understand what is a demultiplexer. Give an example of application of those two. And see if we can really apply a multiplexer provided the problem. In this case, multiple inputs. I only need to use one channel. How do I do that? How do I add those signals so that I can use one channel to transmit them? I can use a multiplexer. I don't want you to dwell too much on the timetables, the truth tables, the logic expressions for this case. For adders, for comparators, I need you to understand the truth tables. For encoders, multiplexers, I need you to understand application. Application, mostly. All right, questions before we move. Very questions, code converters. Multiplexer, demultiplexer, decoder. Nope. Right. Yes.
So basically madhecoder tinoshandisa mumba ndozvaanoshanda achiita.
Decoder.
Yeah,
question.
Wisdom.
Yes.
Yes, that is how it works. It decodes a signal. All right. Mudenga omo. Mune a lot of signals. Mune signal BTV, ETV, ZTV. Decoder way back. This is what I used to know. ZTV. What your decoder does, it selects, okay, today we are working with ETV. It decodes a specific signal. Remote rako, I need this signal. That's sort of your data selector. I need this signal to reach my decoder. Or on a broader term, we have satellites. We use different satellites. How do I put it? Satellite 1, satellite 2, satellite 3. I'm sure different decoders, they use different signals from different satellites, most of them. Satellite dish inokwanisa kutadzisa mabazuva, madokero, depending on the satellite rarushanda now. A decoder can work as well in a way to detect which signal do I want to use. Which signal to use. Without a decoder, it means you have confusion of which signal am I supposed to be using without a decoder. I'm sure there is this simple decoder we are talking of in that big decoder, you know. I'm hoping there is. And I'm hoping once this is something I'm trying to say.
Karimu.
Karimoga.
I understand.
So bigger picture, try thinking that big. Thank you very much for posing that question. Try thinking that big. Ndo menopinda logic design momwe. There is logic design all over that decoder. There is a very small chip with the decoder and the whole thing, probably that's why it's called a decoder. I don't know. Someone to confirm this. I don't know, but my explanation fits though. Any other questions? Nope. 5 minutes. Assignment. Assignment number 3. I want a half subtractor. I want a full subtractor. I want a 2-bit comparator. I also want, what else? How priority encoder works. So for these 3, I want, these are your problems. I want the analysis to the design. From the analysis, I cannot repeat this enough. This will be very useful. You need truth tables. You need logic expressions. You need logic diagrams. I need to see these 3 here. This is our assignment 3. I'll create a Google Drive, photos, PDF. Vamwe vanhu vanosenda maword muchidii kana kusenda mafoto muchisenda multiple documents papapo muchaiona maresults ari kuuya nhama yacho. Don't make that mistake. I'm sure
What's the
Google
due
Drive
date?
due date muri kuya rini pacampus?
of Sunday 13 June.
13 Kuro. That's it. Today the date is
7.
7 week. Okay, fair enough. Sunday. There is your due date. Compress my files again, please. Learn to compress my PDF. Don't send my 20 megabytes. You have the data, yes, but 20 megabytes can be compressed. Google how to compress your documents. Thank you very much. End of the session. We meet on Thursday.
Mjana bani kusini.
Aiwa, bana mnarukopera question. Yenda udara. Whiteboard rangra tende. Watch. Ripo. Okay. That is the question. Take screenshots. Ndimaona ari mugroup. Zvofoeresa izvozvo. Hapana munhu arunzwa assignment iyoyo.
Apamati, how what encoders work?
How priority encoders. How does a priority encoder work? How priority encoders work? How? Voila. I think we're done for the day.
It's 4 questions. That's a